Hey guys, welcome to my channel. My name is Lokesh. I work as a lead architect. So let's continue our book reading series where we are covering chapter 10 of a book called AI Engineering. So as we have discussed that this book has been quite famous in the AI realm, and especially folks who want to transition from some of the other domains to AI engineering, because as we know, AI and Gen AI are new technologies that are emerging. So people would want to move into Gen AI and AI. And for most of us like who work in data engineering, this transition could be organic. We cannot really separate the data engineering projects from the AI projects or Gen AI projects because at the end of the day, Gen AI needs data in order to arrive at the inference or the outcomes. So let's continue our study. So far we have seen that in a simple architecture, you will just query the model and it will give you the response. But we need to have different other components like context, construction. Then we need to have input guardrails, output guardrails. Then we need to have routing, generation, evaluation. Why we need context construction is so that we can get better answers. We can get answers from RAG systems. On the other hand, we need in guardrails because we don't want any personal information to be leaked to these the models, and also we don't want any false responses or responses which are uh, not moral, or they create controversies on top of it. And then comes the routing and the gateway. So gateway is needed because we want to have a single system, where single place where we see how many calls have been made to the models and what is the incoming calls, what are the incoming calls, what are the outgoing calls. And then obviously you need to score the outputs that are getting generated so that that score information can feed into the data that is being generated, and based on that we can get a better response from the model. So that's why we need the scoring. And there are two ways to use the models. One is through calling the APIs that most of the foundation models provide, or the other ones is host the models in your local system, in your cloud infrastructure. You can do that. So let's continue, and we will now talk about reducing latency with caches. So let's do the book reading. Caches has long been integral to software applications to reduce latency and cost. Many ideas from software caching can be used for AI applications. Inference caching technique, including KV caching and prompt caching, are discussed in Chapter 9. This section focuses on system caching because caching is an old technique with a large amount of existing literature. This book will only cover in broad strokes. In general, there are two major systems caching mechanisms: exact caching and semantic caching. So we are going to cover caching, but will not take a deeper dive because of two reasons. One is there is a dedicated chapter to this, and the other reason is caching is not a new term that is in Gen AI or AI applications. Caching has been around for quite a while, and it's applicable to most of the applications, especially the applications where you need a user interface. So the author is saying there are two types of caching that will be focusing on, or he is making us focus on. One is the exact caching, and the other one is semantic caching. So let's read through this. With exact caching, cached items are used only when these exact items are requested. For example, if a user asks a model to summarize a product, the system checks the cache to see if a summary of the exact product exists. If yes, fetch this summary. If not, summarize the product and cache the summary. Exact caching is also used for embedding-based retrieval to avoid redundant vector search. If an incoming query is already in the vector search cache, fetch the cache result. If not, perform a vector search for this query and cache the result. So Couple of important things can be drawn from these two paragraphs. One is that every vector DB would have a cache layer, right? It will have some, data for which that has already been queried, and that would be stored here. So how long these cache sessions are active, that we don't know. Maybe they are persisted forever, or maybe it is based on a user interaction. So that I think we'll have to explore. And the second is that it could only be applicable in case of RAG systems. That is also one of the questions, because RAGs or vector DBs are mostly used in RAG systems, uh, where we have the explicit, or we can customize those vector DBs. But in normal, maybe in normal, when I say normal, I mean to say when you try to use ChatGPT or Gemini, the UIs, I'm not exactly sure if the results would be cached, because all those results would be based on user sessions. So that is where I think whatever we were discussing, if those user sessions have expired, maybe the cached result will no longer be there. Caching is especially appealing for queries that involve multiple steps, example chain of thought and or time consuming actions like retrieval, SQL execution, or web search. Exactly a point that we just discussed. An exact cache can be implemented using in-memory storage for fast retrieval. However, since in-memory storage is limited, a cache can also be implemented using databases like PostgreSQL, Redis, or tiered storage to balance speed and storage capacity. Having an eviction policy is crucial to manage the cache size and maintain performance. Common eviction policies include least recently used, least frequently used, and last first in, first out. So they're talking about various sorts of cache storages that could be used. So in addition to vector DBs, we could also use some of the other DBs like PostgreSQL, Redis, or TS storage, or an RDBMS, based on what we want to do or what sort of data we are dealing with. And then they're saying that in order for caching to be effective, we need to have in-memory storage, which means that the cache results should be stored in your RAM. Just like what happens when you are working in your local machine. If you have some data which is available in memory, that is easy to access. This is a typical uh, data access architecture, where if you want to get faster retrieval, you should have an in-memory storage. One other example could be your Power BI. Let's move forward. How long to keep a query in the cache depends on how likely this query is to be called again. User-specific queries such as "what's the status of my recent order" are less likely to be reused by other users, and therefore shouldn't be cached. Similarly, it makes less sense to cache time-sensitive queries. Time-sensitive queries such as "how's the weather?" Many teams train a classifier to predict whether a query should be cached. So I think let's go back and revise our understanding. So we were thinking that this could be user-specific cache mechanisms, but some of the queries could be, reused by some of the other users. For example, let's say if I'm querying something, how can I, how can I generate a Python code uh, for a Fabinaco series? I think I'm not maybe pronouncing the name correctly. Or maybe how do I generate or give me a Python code for, uh, generating a division by two program. So this could be a common question that some of the others user can also want, which means the results of this query would be cached. So that would remain in the system as long as uh, we have, and that was also depend on the eviction policy. What sort of algorithm we have used. So, for example, FIFO, first in, first out, or least frequently used. And there could be other questions, where it doesn't make any sense to, have them cached. For example, my recent order. My recent order is, recent order number will always be unique. So none of the other users will have the same order number. So that could also be the reason for this. So some of the user specific queries such as what's the status of my recent order, as we discussed, everyone would have their on their own orders, so that it doesn't make sense to save it or cache it. Caching, let's move forward. Caching, when not properly handled, can cause data leaks. Imagine you work for an e-commerce site and user X asks a seemingly generic question: what is the return policy for electronics products? Whether your return policy depends on the user's membership, the system first retrieves user X information, then generates a response containing mistakenly the query for a generic question. Caches the answer later when user Y asks the same question. The cache, yeah. So we have to, take care of these pitfalls. The user specific information, I think, or the PIA information shouldn't be cached. So that was the exact caching where the exact match is made. Let's talk about the semantic caching. Unlike in exact caching, cached items are used even if they are only semantically similar, not identical to the incoming query. Imagine one user asks what's the capital of Vietnam and the model answers Hanoi. Later another asks what's the capital city of Vietnam, which is semantically the same question but with slightly different wording. With semantic caching, the system can reuse the answer from the first query instead of computing the new query from scratch. Reusing similar queries increases the cache's hit rate and potentially reduces costs. However, semantic caching can reduce your model's performance. Understood. So in this case, instead of looking at the exact match of the questions being asked or the prompt, it will try to look at the semantically matching question that is being asked. So that is what it is. Semantic caching works only if you have a reliable way of determining if two queries are similar. One common approach is to use semantic uh, similarity as discussed in chapter. Okay. As a semantic similarity works as follows. For each query, generate its embedding using an embedding model. Use vector search to find the cached embedding with the highest similar score to the current query embedding. Let's say this similarity score is X. If X is higher than a certain similarity threshold, the cached query is considered similar, and the cached results are returned. If not, process this current query and cache it together with its embedding and results. So one question that comes in my mind is, in case of exact caching, you don't need to build the scoring mechanism, the embedding scoring mechanism. So the scoring way of finding whether the query exists or not doesn't happen in case of exact caching. So maybe let's try to Gemini this. And let me ask a new chat. Okay, so exact caching, Gen AI solutions Does it check embedding score? No, exact caching engineer does not typically check the embedding score. Here's why. In summary, exact core caching is a straightforward technique that prioritizes speed, stores and retrieves responses based on the exact matches of the input query. It's like a traditional cache where the key is the query and the value is the response. Guys, this is important. Semantic stores and retrieves responses based on the meaning of the query. It uses embedding to represent the query's meaning and finds similar queries in cache. And this is important. So this key value pair concept is, very important, as I said. So key will always be the question that is being asked, which means even a slight deviation in the spellings of the query that is being asked would result in breaking that caching or making, or what it means is that the system would not look for the data that is already cached. Instead, it would go to the LLM and try to find the answers, which is important. So we understand in this semantic caching that for every query search, the query search and answer for every query there is a embedding and there is a score associated with that embedding. And if a new question is being asked, then based on how close that embedding score is to the original one, that is where uh, the results are cached, and the threshold also defines whether the new caching score should be considered as applicable or should be considered as qualified so that it could return an answer. This is good. This approach requires a vector database to store the embeddings of cached queries. Compared to other caching techniques, semantic caching value is more dubious because of its components are prone to failure. Its success relies on high-quality embeddings, functional vector search, and a reliable similarity metric. Setting the right similarity threshold can also be tricky, requiring a lot of trial and error. If the system mistakes the incoming query for one similar to query, the return response fetched from the cache will be incorrect. In addition, semantic cache can be time-consuming and compute-intensive as it involves vector search. The speed and cost of this vector search depend on the size of your cached embeddings. Yeah. So maybe let's try to break it down. So why it is time consuming is because you have to embed the question that is being asked. Which means some process has to run, uh, and some lookup activity would have to be performed in the vector DB, and that is where it could take time. But for us, if I just talk about using ChatGPT or Gemini, for us, the answers are returned within a fraction of time. So maybe the question that I might need to ask is Gemini using semantic caching? Well, Google hasn't implicitly stated the exact caching mechanism. It's highly likely that it employs a combination of and including semantic hierarchy efficiency. Okay. So maybe Gemini is a closed model, so that's why they are not returning this answer. So maybe I should, change this and maybe just ask deep seek using semantic caching. They do also perform or employ a form of caching that leverage the context of previous and which has similarities to semantic. Here's how caching works. Okay, so maybe just go through how this works. So since DeepSeek is an open model, so we should be able to get the answer. So it's not exactly semantic caching, but what they do is uses a hard disk cache that stores the context of previous requests. This includes both users' prompts and the model responses. When a new user comes in, DeepSeek checks if it has only overlapping prefixes with previous requests stored in the cache. If there is an overlap, the system retrieves the common prefix from the cache. If retrieval of the overlapping prefix from the cache is considered a cache hit, it saves the system from reprocessing that part of the conversation. So it uses prefix matching when a user requests the prefixes. So maybe some part of the questions that are being asked. Caching, while not experiencing, incorporates principle of semantic by leveraging the context of past interactions. So maybe this is what I think Gemini or ChatGPT also does, because DeepSeek is also built on same set of architecture, although the way it tries to retrieve the answers is slightly different, and that's based on MOE architectures, which is I think OE stands for of experts. I'm not able to recall. Mem What does MOE stand for? Maybe let me search that. What does MOE stand for? MOE stand for with respect to Gen AI. Mixture of experts. Yeah, so it's based on mixture of experts. This is what I was looking for. Okay, let's get back to the syllabus. So then with the added cache system, the platform looks like we get a keyword cache, a KV cache and prompt cache are typically implemented by model API providers. So they aren't shown in this figure. To visualize them, I'd put them in a model API box. There is a new arrow to add generated responses to the cache. So you have your query. So it would, okay, that makes sense. It would go to the cache and it will try to generate the response. The platform KV cache and prompt cache are typically in cached response. What's a KV cache? KV cache and prompt cache are typically implemented. Keyword cache by model API providers, so they aren't shown in this image. To which I put them in the model API box. There is a new arrow to add generated responses to the cache. What's a KV cache? I didn't understand that. What's a cache? The word of allowing generative model KV cache is a clear technique used to signal the speed of the processor. There is a breakdown. It's more interesting images. If you're writing a long essay without a KV cache, you would have to read the entire essay every time you write a new sentence to make sure it fits. Key value cache. Simply refer to the notes. You can simply refer back to your notes. The cached KV matrices. Quickly understand the context and write the new sentence. Using KV cache is a critical optimization that enables to generate text much more efficiently. It's a key factor. Imagine you are writing a novel out. You have to reread the entire essay every time you write a new sentence to make sure it fits. You can simply refer back to your notes to quickly understand the context. So maybe the KV cache is different. Cache are typically implemented so they are not bound. So KV cache is I think KV cache is a different concept. It's not similar to the custom cache that we are going to build. That's fine too. I'll put them in the model. There is a new arrow to add the cache. Okay, let's not maybe confuse with KV cache. I think the author says that this is something that a model API provider should have, and it's mostly applicable on the model API side. But with the cache that we have read, this is how it looks like. When you query it, it will first check in the cache whether that exists or not, and also um, if it is a vector DB, then there could be a case of a semantic cache, and it will see whether the query being asked is similar to the query that is cached, and then it will return you the output. So that is how it is presented. Okay, cool guys. Another good session. I gained a lot of things from it. We tried to counter read some of the concepts, which means that we didn't take everything for granted. So we went online and tried to Gemini this or Google this, which is a right way to study the things. So we'll meet in the next video, guys. Till then, take good care of yourself, and thank you for joining.